Now that we've discussed the graph of exponential functions and transformations of exponential functions, we'll do the same thing about logarithmic functions. Recall that log base a of x is the inverse of a to the x, so the graph of log base a of x will be the reflection of the graph of a to the x over the diagonal line y equals x. That's a line with slope 1. And our exponentials, remember, look something like this, or, different versions of those. And if I reflect that curve over this line, y equals x, I end up with my logarithmic function. Always helpful to remember that. Let's discuss some of the properties of these. Logarithmic functions can look a little bit different, but they all got the same general flair to them. They all go through this point right here, 1, 0. At least the base, log base a of x, where I'm not adding or subtracting anything yet. It's going to go to this point 1, 0. If I have a smaller base, I increase more quickly over here. The larger bases increase a little bit more slowly. But they still have the general shape to them, this kind of movement for all of them. So we can talk about these properties in generality no matter what my base is. So let's first talk about the domain and the range. The domain is all the x values. And if I think about just one of these graphs at a time, not all together, but just one at a time, a general log base a graph, my domain, all the x values I have graph for, actually just have graph on the right side of my x-axis. My domain here is going to be 0 to infinity. We'll put a parentheses on that 0 because, well, we never touch that y-axis. I don't have any actual points on this. So we'll put a parentheses to say we approach that, but don't exactly touch it. My range, however, I can get all sorts of y values. I get my negative y values from this part of the graph. I get my positive y values from this part of the graph. I can highlight my entire y-axis and get graph associated with that. So I would say that my range is going to be negative infinity to infinity. For all logarithmic graphs like this, my x-intercept is going to be the point 1, 0, no matter what my base is. And there are no y-intercepts. We do not touch the y-axis. We also have a asymptote here. In this case, a vertical asymptote guiding the behavior around 0. Let's sketch that in. Again, we like to use dashed or dotted lines for asymptotes. In this case, the y-axis is serving the role of my asymptote. And the equation of the y-axis is the line x equals 0. This graph is also 1 to 1. We check that using the horizontal line test. If I pass a horizontal line through this, I never touch more than 1 point, which tells me, yes, this is 1 to 1. Which makes sense. If a function is 1 to 1, it has an inverse. And we kind of define this as being the inverse of exponentials. And so it better also be 1 to 1 since it is itself an inverse. There's no symmetry related to logarithmic functions. It's not symmetric over the x-axis or the y-axis. We might get it by reflecting an exponential over a line, but the graph itself doesn't have any inherent symmetry. If we think about whether our function is increasing or decreasing, as long as my base is greater than 1, which is almost always what we're going to think about, my graph is going to be increasing. This is going to be increasing on the interval 0 to infinity for a greater than 1. I say it's increasing on the interval 0 to infinity because those are the x values that correspond to where my graph is increasing and turns out to be the entire domain. The end behavior, well, we don't really have a negative infinity end behavior. We just kind of have like a approaching 0 end behavior. And then we have a positive infinity end behavior as well. So we might say that the graph rises on the right and falls as the graph approaches x equals 0. That's a way to describe what's going on up here. It's rising to the right and falls as we approach 0. So these are the general characteristics or properties of a logarithmic function. You should be familiar with logarithms enough that you should be able to draw a rough sketch and say, in general, this is what a logarithm looks like. If we have a different base, it might kind of be up more or a little bit more slowly, but you should be able to draw a sketch that has the correct in behavior and the domain and range and x-intercept, and just kind of in general call that the graph of a logarithm. It's kind of like a square root graph. That looks more like this. It's a little bit different though, because the square root graph does have that, it touches the origin at 0, 0, and a logarithm doesn't do that. This graph over here doesn't have the correct in behavior. So this is not what we're thinking about. All right, now that we've discussed the properties of logarithms, now we can translate logarithms just like we were trying to translate and transform exponential functions. We can transform logarithmic functions with the exact same rules for placement. It looks a wee bit different just because my functions themselves are a wee bit different here. But in general, we follow the same rules. We could have a vertical stretch by multiplying by a number in front. We could have a horizontal shift by adding or subtracting right next to my x inside of my logarithm. And we could have a vertical shift up or down by adding away from my x outside of my logarithm. And just like before, if a is negative, we would have a reflection over the x-axis. So we have two examples here, one where we want to take the equation and graph it, and another where I'm given a description and want to write the equation. So I want to sketch the function negative log base 2 of x minus 1. And I might start with a guiding sketch to remind me what the graph of log base 2 of x looks like. So what kind of translations do we have here if I want to think about the graph negative log base 2 of x minus 1? This x minus 1, the minus 1 is going to shift it to the right 1, and this negative in front is going to reflect over the x-axis. So in the end, if I take each point and move it right 1, I'm going to have something like this. And then if I reflect that over the x-axis, I'm going to get points like this. And instead of approaching negative infinity down here, I'm going to be approaching positive infinity. My graph will look like this. So this is the graph of negative log base 2 of x minus 1. Let's also think about the domain, the range, and the asymptotes. The domain is all the x values that have graph, and I stop having graph at a certain value here. I think that value is going to be 1 when I've shifted. It used to be kind of 0 to infinity, but I moved all that right 1, and so my domain is going to be 1 to infinity, but I won't include 1 because I don't actually touch it. My range, all my y values that have graph, well, I have all my highs and I have all my lows, and my entire y-axis has graph corresponding to it. So I would say that my range is negative infinity to infinity. And my vertical asymptote, if I were to sketch that in with a dashed line, would look something like this. That line x equals 1 is going to guide the behavior here. Right, we took that equation x equals 0, which is our normal asymptote, and I have shifted it right 1, and I've reflected across the x-axis, which if you take a vertical line and reflect it over the x-axis, you still have that same vertical line. So just the shift right has affected that. All right, the last thing we'll talk about is going the other direction, going from a description to an equation. So here I want to write the equation for the common logarithmic function, stretched vertically by a factor of 2, shifted left 4, up 3, and reflected over the x-axis. All right, we have a lot going on here. The first thing I want to think about is what is the base of this logarithm? Anytime I write a logarithm, I have to determine what the base is. The common logarithm, remember, is base 10, and we actually don't write it. So because this is the common log, that really means base 10, but I'm just going to write it as log, and I'm not going to put a number there. We're going to know that that really means that down here there's a 10, but we're not going to write it. All right, so my common logarithm, I want to stretch it vertically by a factor of 2. Stretching vertically is just going to be a multiplier out in front of my logarithm, which means I'm going to have a 2 here to be a vertical stretch. If I want to shift it left 4, well, the left 4 is what goes in with my x. So I either would put a plus or minus 4 in there, and it's going to be a plus 4 to move it left. To make it go up 3, I need to write a plus 3 somewhere, and I need to write that plus 3 outside of my logarithm. So I could maybe put that out in front and make it 3 plus, or I could put it at the very end and put plus 3 after my logarithm. Either one is just fine as long as the 3 is not inside the parentheses of my logarithm and it's not multiplying by that 2. The last piece we need in order to reflect this over the x-axis, we need to put a negative out in front of my function. Not in front of the x, but in front of the function. So I'm going to put a negative here, make that multiplier a -2 instead of a 2. And that will both stretch it vertically by 2 and reflect it over the x-axis. Again, these are the same kinds of things that we would do for exponential functions or square root functions. We just have a different function with it. If I had asked almost the exact same question, but it said, write the equation of the natural exponential function, which has been stretched vertically by a factor of 2 and shifted left 4 and shifted up 3 and reflected over the x-axis, it's going to look really, really similar. But instead of having the function log, I'm going to have the function e to the x. It would look like this. I would still have a -2 out in front, and I would still have a plus 3, and I would still have an x plus 4, but that x plus 4, instead of being inside of a logarithm, it would be inside of the exponent on an e.